Hi everybody. This is fourth in the series of lectures of simple machines. In this video we are going to talk about speed multipliers. So far we have seen what a force multiplier is. So summary so far, the last three videos what we have seen. Mechanical advantage is given by output force by input force, which is load by effort. That's by definition. And if your mechanical advantage is greater than 1, we say it's a force multiplier. So that means that your output force is going to be, your output force is going to be a multiple of input force by a big number, right? Greater than 1. Or in other words, your output force would be greater than your input force. And in an ideal machine, your ideal mechanical advantage would be equal to the length of the effort arm divided by the length of the load arm, but we know that mechanical advantage is usually less than your LE by LL, right? So usually this is less than this quantity. And your velocity ratio, we found that is by definition equal to dE by dL, and through the approach of similar triangles we found that that's equal to LE by LL. So in other words, your ideal mechanical advantage is equal to velocity ratio, but usually your mechanical advantage is less than velocity ratio. So that's what we have seen so far. In this video, we are going to do a problem, and the problem is as follows. So here is a picture of a person making dal. And let's say the load that he is carrying is about 10 kilogram force, and this is his fulcrum, and this distance, the distance that this is there is about this. Let's take this is approximately 200 centimeters, and the effort that he is putting in is about 1/5. That's about 40 centimeters. So the question is, A, please find your effort, B, find your mechanical advantage, and C, find your velocity ratio. Please take a pause and try to find the answer for all this. If you got the answer as 50 kilogram force is the effort, and mechanical advantage is 1/5, and velocity ratio is 1/5, you're absolutely right. So how do you get this? So A, you know that ideal mechanical advantage is equal to load by effort, and that's your mechanical advantage is load by effort, and your ideal mechanical advantage is equal to LE by LL. So that's equal to your load by effort, and your load is about 10 kgf by effort is equal to the load of the effort arm is 40 divided by 200. So your effort would be 50 kgf. Now your mechanical advantage is load by effort, and that is equal to your load is 10 kgf, and your effort is 50 kgf, and that's 1/5. And similarly your velocity ratio is distance moved by the effort arm by distance moved by the load arm, and that's equal to LE by LL, and that is equal to 40 divided by 200. That's also equal to 1/5. So of course this is an ideal case, so your mechanical advantage and velocity ratio are both same. So please don't confuse when I say ideal mechanical advantage. You can, if you feel that's confusing, you can discard this I completely, and you can imagine this as mechanical advantage, right? So this is just to say that you can use this equation only when it is an ideal case. So what do we infer from this? So your inference. Here is a case when mechanical advantage is less than 1. That implies that your effort is more than your load. So you have to put in more effort. But what is an advantage of this is that if you look at your velocity ratio is less than 1 here, what does that imply? That implies that your effort, the distance moved by the effort arm, which is this is your effort arm. Your distance moved by the effort arm would be lesser than the distance moved by the load arm. So in this particular case, he wants to swirl this dial. He wants to swirl this dial, right? So you swirl this dial, and the distance moved by your load would be far greater than the distance moved by your effort. So as you move smaller distance in your effort, you will see that you cover a large distance in your dial, right? Or in other words, your speed at which your load is moving is much higher than speed at which your effort arm is moving. So we call this as speed multiplier. In VR is less than 1 means speed multiplier. So when we say speed multiplier, we actually mean your output speed multiplier. So which is basically at this point your output, which is your dial, which you're swirling around. So we call this as speed multiplier. So velocity ratio less than 1 is a speed multiplier. That's a key message. Here is one slide that puts all that we have learned so far together. So your mechanical advantage is load by effort, and in ideal case, mechanical advantage is LE by LL. Your velocity ratio is input force distance by output force distance. Of course, for all these, your context is very important. So here's the context, which is this is your load, and this is your distance traveled by the load, and this is your effort, and this is the distance traveled by your effort, dE, and this is your effort. Your effort is in this direction, of course, and then this is your fulcrum, and this is your length of the effort arm, and this is your length of the load arm. So this context is very, very important along with the equation, and your ideal mechanical advantage is equal to the velocity ratio, and your usual, but in general your mechanical advantage would be less than velocity ratio. We have seen that, and if your mechanical advantage is greater than 1, it's a force multiplier, and if your mechanical advantage is less than 1, it's a speed multiplier. And both these cases, the speed multiplier, force multiplier, we mean to the output, with reference to output, right? So in other words, we can say output force multiplier or output speed multiplier. Output force multiplier when MA greater than 1, and output speed multiplier when MA is less than 1.